Hello everyone, myself Dr. Vipul M. Patel from Dr. Subhash Technical Campus. Today I am here for another lecture of the production technology, and today we are going to discuss about the chapter number 2, thermal aspects in machining. And today we will learn in this session about the source of heat generation, heat distribution, cutting fluid and its properties, advantages, disadvantages, characteristics of the cutting fluid, and final topic, that is measurement of chip tool interface. See, we will start from the source of heat generation in machining. See, we have already performed different types of operation in the different metal cutting lathes, drilling, milling, shaper, planer, slaughter, etc. And during that metal cutting operation, heat is generated. So we can say that which are the sources of the heat generation during the machining. So I hope there is mainly 3 zones where heat will generate during the machining. Shear zone, that is about around the shear plane. Friction zone, that is around the chip tool interface. Third one, that is tool work interface zone, which is around the flank face of the tool. So mainly there are 3 zones, and we can say that there are the main 3 zones which is called the sources of the heat generation. So shear zone, it is the region in which actual plastic deformation of the metal occurs during machining. So with the use of the figure, you can easily understand where is the cutting tool and how we are removing some metal or material from the work in form of chips, and where is the shear plane. So it is nearer to that, and it is one of the region that which is actual plastic deformation of the metals occur during the machining. It is called shear zone. So due to the shear deformation is generated. So as we discussed, लोहे से लोहा टकराए. So it is very easy to understand. Heat will be generated during the machining. A portion of this heat is carried away by the chip. In this portion, heat is carried away by the chip, due to which its temperature is raised. That's why temperature will be raised. The rest of the heat is retained by the workpiece. So remaining heat, which is not away by the chip, carried away by the chip, remaining or the rest of the heat is retained by the workpiece. It is known as primary deformation zone. We can say that shear zone is also known as a primary deformation zone. Now friction zone. As the chip slides upward, along face of the tool, friction occurs between their surface. When some material or metal will remove from the workpiece in the form of chips, and chip slides upward against the cutting tool along the face of the tool, at that time some frictional action will occur between their surfaces of the chip and tool, due to which heat is generated. That is the fact. And a part of this heat carried by the chip. So some part of this heat which is carried away by the chip, which further raise the temperature, the remaining temperature of the chip, and the rest transferred to the tool and the coolant or cutting fluid we are using during the operation. So this area is known as secondary deformation zone. So in another language also we can say friction zone is known as a secondary deformation zone. So the amount of the heat generated due to the friction increase with the increasing cutting speed. Whenever we are increasing the cutting speed, our tool life will be decreased. Why? Because always if we are increasing the cutting speed, then heat will also increase, no doubt. So it is not appreciably affected with the increase in the depth of cut. The relation between the cutting speed of the heat, another relation of the depth of cut and heat, and third one, that is the when the feed rate is increased, the amount of frictional heat generated is relatively low, but in that case the surface obtained is inferior. Right? So this is the friction zone. Third one, that is tool work interface. So that portion of the tool flank which rubs against the workpiece is another source of the heat generation due to the friction. Another portion where heat will be generated during the machining, that is tool work interface, where tool flank which rubs against the workpiece, the flank of the tool. We already discussed about the tool geometry, and in that we have already discussed, or we have already studied about the flank. The flank of the tool which rubs against the work surface is another source of heat generation due to the friction. So this heat is also shared by the workpiece and the coolant used. This heat is also shared by the tool works and coolant used. It is more pronounced when the tool is not sufficiently sharp. When this type of heat will produce, at that time we can say that when the tool is not sufficiently sharp. Means if we are using a blunt tool, then this type of heat will introduced. Right? This one is a third one, tool work interface. Distribution of heat now. Distribution of heat between chip, tool and workpiece during the cutting. So if we are drawing a graph of the heat generated in machining, which is in the percentage, versus cutting speed, you can easily understand with the use of the graph. When our cutting speed will increase, definitely heat generated in machining by percentage wise, it will definitely increase. Now you can see in the percentage how much heat will distribute during the machining operations. So in this figure we already saw the distribution of the heat generated during the metal cutting. If we are neglecting the heat flowing to the atmosphere, some of the heat, if we are neglecting, which is flowing into the atmosphere, then on an average we can say about 70% of total heat is carried away by the chip. Those material we are removing from the workpiece in the form of chips, definitely on an average near about 70% of the total heat is carried by the chip, and remaining about 15% is transferred to the tool, cutting tool. So 70 plus 15 is equal to 85%, and remaining 15% to the workpiece. If we are neglecting the heat flowing up the atmosphere, then the calculation it is like that: 70% of the total heat is carried away by the chip, about 15% is transferred to the tool, and the remaining 50% to the workpiece. Right? With an increase in the cutting speed, a higher amount of heat is absorbed by the chip and lesser amount of heat is transferred to the tool and the workpiece. So as we calculated it, near about 70% of the total heat is covered by the chip. So we can say that with an increase in the cutting speed, the higher amount of the heat is absorbed by the chip, and lesser amount of heat is transferred to the tool and the workpiece. That is final. It is an obvious advantage in the high speed machining. Whenever we require very high speed machining in the mass production, then it is very most important advantage we can say for these high speed machining operations. Some of the heat generated is also carried away by the flowing cutting fluid whenever it is used. So some of the heat generated is also carried by the flowing cutting fluid if we are using different cutting fluids. The shear angle also affects the heat generation, and a larger shear angle leads to a smaller heat generation in the primary deformation zone, right? So this is the amount of heat generated. If you want to find it, you can say calculative base if you want. In the metal cutting, the amount of heat generated per unit of the time is given by the thermal equivalent of the mechanical work done. Mechanical work done is given by the cutting force into the cutting velocity. So Fc into Vc. Now if Q be the amount of the total heat generated in the cutting the metal, then how can we find it? Q is equal to work done divided by 427. So in place of the work done we can write Fc into Vc, because cutting force into the cutting velocity divided by 427 kilocalorie per minute. So this is the formula to find out the heat generated during the machining. If we have cutting force in kg, if we have cutting velocity, then we can definitely find the work done, and with the use of that we can easily find the heat generated during the machining. Now on the cutting fluid. Introduction about the cutting fluid. The use of the metal working fluid is essential in the all metal working operations. In metal machining, a lot of heat energy is generated, proves harmful to the tool or work of both. So this type of fluid help in minimizing this adverse effect, thus help to increase the tool life and surface finishing. So as we discussed earlier, tool life is directly proportional to the cutting speed. If we are increasing the speed, then definitely heat will increase. So heat will increase, then tool life will be decreased, right? So this type of fluid which can help in minimizing the adverse effect of the heat. These are the functions of the cutting fluid. To cool the tool and workpiece. If we are using the cutting fluid, then it will help to cool the tool and the workpiece. To provide the lubrication between the tool and the workpiece, and the tool and the chip also, because it acts as a lubricator also, right? In between chip and tool, work and tool, and tool and work. So to prevent the adhesion of the chip to the tool or work, both. So it can prevent also adhesion of the chip to the tool and work or both. It will reduce the friction also. So it is used to reduce the friction also. It can protect the corrosion. So we are using it to protect corrosion. To wash this chip away from the tool. It is also used to wash the chips which are removing from metal or material, right? Qualities or characteristics, we can say, or properties of the good cutting fluid. High heat absorption. Whenever heat will increase during the machining, then maximum heat it can absorb, right? So we can say that it is one of the good quality of these, or good characteristics of the cutting fluid. Good lubricating to produce low coefficient friction. So it is, as we discussed in the previous slide, it acts as a lubricator also. So good lubricating property is also there. So with the use of that, we can easily decrease the friction in between work and tool. High flash point that can hazard the fire. So it is a good property also, which has a high flash point, so that can hazard the fire. Stability is also good. It is a neutral, so as not to react the chemically. If the chemical or the cutting fluid will be on our hand during the operating, then it is not react chemically, and it is not any type of effect on our skin also, right? It is odorless, so as not to produce any bad smell when heated. Some fluid we have seen that when it will be hot, then some bad smell will come from that, right? So it is odorless, no any bad smell even when heated it also. It is a harmless, so as not to the effect on skin of operator as we discussed. Then non-corrosive to the work or the machine. So if it is on the machine, if it is on the work, if it is on the tool, then it will not affect that particularly, right? It is a non-corrosive. So transparency is also there. So with the use of that, we can easily see the operation, so that the cutting action of the tool may be observed, we can say. Low viscosity is also there, so it is giving permission for the free flow of the fluid. So viscosity is not there, or low viscosity we can say. Low price to minimize the product cost. So cost wise, if we are thinking about that, okay, it is very it is not cost wise it is not good, and it can increase the total total cost of the product, but not like that. Low priced to minimize the production cost also. So these are the different types of fluid which we are using the different machining, different operations. Which type of material we are cutting with the use of the different operation on the different machines. So on the basis of that, we have to select the particular cutting fluid, which type of cutting fluid we want to use. So neat oils, mineral oils, fatty oils, and combination of the boys, which is also we can include in the neat oils. Oils generally we are using here. All of you, I hope all of you are seen that different types of oils that we are using in the automobile vehicle also, right? So mineral oils, fatty oils, or combination of the minerals and fatties, right? Then water soluble oils. Water soluble oils are blends of the mineral oils and emulsifying agents. So what is water soluble oils? It is the blends of the mineral oils and emulsifying agents, so which can help easily to flow, free flow on the chip tool interface. So with the use of that, we can easily cool the tool, cool the cutting fluid, etc. Now synthetic coolants. So synthetic coolants are non-petroleum products which are blended with the water in the ratio of 50 to 250% of the water for each part of the chemical, right? It is synthetic coolants, which is in which we are not using any type of petroleum products, and which is also we can say which is blended with the water in the ratio of the 50 to 250% of water of the each part of the chemical. Next thing is a gaseous fluid. So mist is the most commonly used gaseous fluid. Gaseous like carbon dioxide, freon, helium have been used for the special applications. These are the gaseous fluid. If we are using a fluid like gaseous, or which is a mixture of the gaseous, which a mist is also a gaseous fluid, then it is called, or we can include it in the gaseous fluid, right? These are applications of the cutting fluid. So if we are performing the turning operation, then which fluid or which cutting fluid I am suggesting to you, that is emulsions or straight oils. So cutting conditions and other requirements we have to remember and keep it in your mind. Selection of the cutting oil depends upon the cutting speed, feed, and material being turned. So which type of material you want to turn, it depends. Then sewing operations, I am suggesting to you soluble oils. And what is the cutting condition and other requirements? Cutting is required for cleaning the saw teeth, carry away and heat generated, and prevent the adhesion of the chips. Next thing is the tapping and threading. So what is the cutting condition and other requirements? Main requirement is the lubrication in the tapping and threading operations, as the cutting speed are very low. So active type mineral fatty oils, of course, occasionally emulsions of soluble oils are also used. Next thing is drilling and boring. Both can perform in the same machine. So what is the cutting condition? The requirements are the lubrication and the cooling both, so as to avoid the chatter, minimize heat generation and cool the tool and the work. I hope all of you have seen this operation, drilling and boring. So in this, directly we are removing some metal in the form of hole, in the form of chips, and I want to make a hole on this workpiece. So in that we have to use soluble oils, right? Next thing is reaming operation. So cutting condition, main requirement is lubrication. So in that we are using soluble oils. Automatic machining, console or multiple spindle automatic lathes, turrets or capstan lathes. What is the cutting condition and other requirements? That is, higher speeds are involved and a large number of the different types of operations are performed. So high viscosity active cutting oil with some fatty oils we can use, because at that time we required cutting fluid with a high viscosity, right? Next thing is a broaching. What is the cutting condition and other requirements? That is, heavier cuts are taken. Heavy active type cutting oils, particularly horizontal internal broaching, we can use. Shaper and planer, or shaping and planning. There is no any extra cutting condition requirements we can say, but usually there is no requirements to use any types of cutting fluid or cutting oil. In operation, the common requirements include the cooling, lubrication and prevention of the tool chatter, because we are cutting the gear with the use of this milling operation. So we have to use sulfurized mineral fatty oils or emulsions in the ample quantity, right? Thread rolling. There is no requirements or cutting condition we can say. Straight mineral oils or emulsions. Next thing is gear cutting and saving. So it is also there is no requirements or any cutting conditions. So active type minerals and compounds we can use. So now on measurement of chip tool interface temperature. It is generally measured by the tool thermocouple technique, and this technique is based on the fact that EMF, or we can say electromotive force, is generated at the interface of the two discs of metal when the temperature at the interface changes. So the three laws of the thermoelectrically which are applicable to thermocouple. So in that, the EMF in a thermoelectric circuit depends only on the difference in temperature between the hot junction and the cold junction, and is independent of the gradients in the parts of the making of system. So the EMF, electromotive force generated, is independent of the size and the resistance of the conductors, we can say. If the junctions of the two dissimilar metal is at a uniform temperature, the EMF generated is not affected by the third metal. But in the both metal, temperature will be difference than which it is at the same temperature used to make the junction between the first two, right? In another language also we can say, in the thermocouple, two dismissional but electrically conductive metals are connected at the two junctions. Then whenever one of the junction is heated, the difference in the temperature at the hot and cold junction produces a proportional current which is detected and measured by the millivolt meter. So in the machining, like turning the tool and the job constitute the two dissimilar metal, and the cutting zone function as the hot junction, the average cutting temperature is evaluated from the MV after through calibration for the establishing the exact relation between the MV and cutting temperature, right? So the EMF is generated is directly proportional to the change in the temperature and can be easily measured with the suitable measuring instruments or recording the device with the use of the different recorders. The setup used for the measurement interface temperature is also, you can see in the figure. This is the schematic diagram of the measurement of the chip tool interface temperature, and it is called thermocouple technique. So in that we are using workpiece tool, insulation, millivoltmeter, mercury cup and disc. So how the setup is there, you can see. The contact point between the tool and chip represent the hot junction. You can see figure. While the ends between the job and tool are assumed to be far away and constitute the cold junction. So decided the hot and cold junction. Now you have to proper insulation is provided at various points to ensure the measurement of the correct temperature. If we are not provide a properly insulator, then we cannot find the exact or correct temperature measurements. So for that purpose we have to provide the proper insulator at the various points to ensure the measurement of the correct temperature. So a suitable indicator or recorder is connected in the circuit to record the EMF or electric force which is generated. It is the setup of the calibration of chip tool interface, or we can say thermocouple technique. So this is the insulator. This is the insulator. This is a coil. This is the lead bars. This is the cutting tool. It is a copper wire. It is aluminium. It is a potentiometer and it is a recorder. And this one is a chip. This is the calibration, or we can say setup for the calibration of the chip tool interface or thermocouple techniques. See, ordinary copper wires can be used to connect the recorder since the ends are at the room temperature and do not cause any error. As we seen in the previous slide in the figure of the setup or calibration of the chip tool interface thermocouple technique. So in order to get temperature value corresponding to the EMF or electromotive force value recorded, a calibration setup is shown in figure. It can be used. So as the lead bar is heated gradually with the help of the heating arrangement provided, the electromotive force generated by both the thermocouple recorded simultaneously. So the calibration chart for the chip tool thermocouple can be easily prepared by finding the temperature value corresponding to the electromotive force value. So this is the principle of the thermocouple technique. So in the thermocouple technique, two dissimilar but electrically conductive metals are connected at the two junctions. Whenever one of the junction is heated, the difference in temperature at the hot and cold junction that we have already decided in the first slide produce a proportional current which is detected and measured by the millivoltmeter that we are using to measure the temperature between chip tool interface, which is also important for the measurement of the temperature by the millivoltmeter. Thank you all.